So today we're doing a rather simple exercise, and we're going to be graphing graphs with limited ranges. And now, one of the things that we want to notice is that when we limit a range, and we limit any graph, we're probably going to want to draw it in pencil because we're going to be doing some erasing. But furthermore, a range limitation has a minimum point and a maximum point. What a lot of people like to call, let's call this a floor and a ceiling. So we have a floor and a ceiling. Now, these almost are always because of some limitation in the cause and not the cause itself. So a good way to look at this is by saying, hey, my Geiger counter has an upper limit. It has no effect on the graph, no effect on the actual radiation, but my Geiger counter can only record up to a certain range and then the graph quits. And so that's why we say there's a ceiling. And it's a limitation of the technology and not the actual cause of what you're trying to measure. Furthermore, when we look at limited ranges, one of the things we'll eventually go through is in calculus, you're going to be looking at what we call limits. And so when a graph starts to spiral upward, so let's take a look at, if I were to draw just a sample graph and say, hey, my graph is going up, 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 but it's starting to taper off. At some point, that graph is going to flatten out. So after some amount of time, where is the point where we can assume that that graph is flat? And we're going to say, okay, that graph flattens out at some y value. What is that y value? And that's basically once we get to infinity. Right now, we're not dealing with curves, we're dealing with straight lines, but the concept is eventually we will get to some sort of limited range. So let's jump into this. So we recommended that we graph this in pencil because we are going to be doing a good bit of erasing. So when we start, we're going to say, okay, I have a line of y equals negative 6x plus 2. Go down 6, 2, 4, 6. Wait, 2, 4, 6, yep, over 1. So I have a graph that looks like this. Let me grab my ruler. So I have a graph that goes all the way up and all the way down, but I only care about values where y is less than 4. And so one of the things that you don't need to do is you don't need to draw the limit itself. You don't need to draw the boundary, but I've noticed that students tend to get a very good image of what's going on with the boundary. If I say y must be less than 4, I'm only looking at values down here. I am no longer dealing with any values that are greater than 4. So I'm going to get rid of this. And that goes away. Might need a no eraser. The only part of the graph that we keep is this lower part down here. So we have our line. Now the boundary itself is an open circle because I'm not actually including the boundary. Y is less than 4, not equal to 4. So there's our graph. We have another one. So also to use our terminology, that would be a ceiling. It can't go above that, it's stopping. This one's gonna be a floor. So if I take my line and I say, okay, start my point at -1, and I go up 2 over 3, down 2, back 3, I get a line that looks like this. Right there. But again, I'm only concerned with the values that are greater than -4. So what I'm going to do is I'm going to say, hey, only greater than -4. Only those. I don't want any values below -4. So I don't want this little piece of the graph. So I'm going to erase it. And again, what I've said a lot of students seem to enjoy doing is they enjoy putting a barrier. Y must be greater than or equal to -4. Now, the thing that I think about the barrier is that it should be a solid line. For some reason, a lot of students like to draw a dotted line no matter where the barrier is. I think because they know that it doesn't need to be drawn. But in this case, I'm going to go ahead and I'm going to draw it all the way. We erase the part below there. I'm only concerned with the part of the line that's above that barrier. And I'm actually going to include the barrier itself, which is why I like to draw a solid line. It shows me that it starts here and goes up. And there we go. And the last type is what happens if I don't have just the floor or just the ceiling? What happens if I have both? Well, it's no big deal. We graph it like we always would. I put a point at -1, and I have a slope that goes up 1 over 1. And so it's a perfect diagonal. Let's go ahead and get this drawn. Perfect. But now what I'm going to do is I'm going to say, hey, I'm only dealing with y's that are greater than -2, which means anything -1, -2, anything down here, I'm cutting it off. And at the same time, y must be less than 5. So I'm going to come up here and say, hey, 1, 2, 3, 4, 5. I actually don't even see it. So unfortunately, what I'm going to have to do is I'm going to have to start over on this because I can't see the barrier. You might be able to keep going because you might have a graph with more than 5 spaces. I'm going to have to start all the way over. So I'm going to say, hey, my graph is by 2's, which means I start right here. Oop, doing that in pen. Not going to be able to erase if I keep doing that. Here we go. Cut my line. I'm going to erase anything below -2, which in this case is a lot higher up. Because in this case, my barrier, y must be greater than -2. And then I have another barrier at 2, 4, 5. Y must be less than 5. So I'm going to have to erase everything above that barrier, which is going to leave me with a very limited graph. It's between -2 and 5, neither of which is included. That's all the graph that I have. That's it. So, the question that you might ask yourself is, does that logic work with other graphs? What about an absolute value? And the answer is, yeah, it does. So, with an absolute value, I know this absolute value has been shifted down 4, so 1, 2, 3, 4. And I have a perfect diagonal going up over here, and a perfect diagonal going up over there. But I'm only going to deal with y values greater than -2. So what I'm going to do is I'm going to say, hey, y must be greater than -2, which means I'm only dealing with values above that. So I'm only going to deal with this piece over here and this piece over here. I'm not actually going to include the barrier, so both times I'm going to include open circles, and I'm just going to go ahead and get rid of this lower piece down here. So does it work for an absolute value? Of course it does. You're just going to get 2 pieces. You might not realize it's an absolute value, because what happens if I only get that little pointy piece? Well, no big deal. Just take off the part of the graph that doesn't work. This is an absolute value that's been shifted to the left too. So 1, 2, and it opens downward. Although I noticed that because I have a -3, that may or may not fit on my graph. So I'm going to go ahead and preemptively make this graph by 2's. And I'm going to say, hey, left 2, and it opens down. Don't need to draw that thick. I'm going to be erasing a lot of this. So in this case, y has to be less than -3. Draw my barrier right here. Y must be less than or equal to -3, which means that I'm only dealing with the lower portion of this graph. Perfect. And I'm actually going to include my 2 points. And so this little piece right here, don't need it anymore. That is a part of the graph that is greater than -3. We don't care, we don't want it. Perfect. And so our last example is an absolute value that has both a floor and a ceiling. So again, I see that I have a value at -5, so I'm going to do these by 2s. This just allows me to fit everything I need onto the graph. So up 1, I go down 2 over 1, and I go ahead, and when I graph this, because I'm graphing at in-between points, I have that. I'm going to say I want it between -5 and 0. So 2, 4, 5. So y must be greater than or equal to -5. It's got to be bigger than that line. And y must be less than or equal to 0. Which means that I don't have the point, but I also don't have these extended lines all the way down to forever. I have what looks like 2 line segments that are on a collision course. Get rid of the unnecessary parts of my graph. I don't need the vertex, I don't need those legs. And there we go. That's how we graph an absolute value with a floor and with a ceiling. So today what we're doing is we're going to be graphing a system of equations. One of the big things we've spent the past several parts on is how to graph a line and how to graph several other types of lines, so that when we look at a system of equations, we're solid on that front. And a system is basically just when 2 or more equations cross paths. A solution is the point or points where they cross. And we'll see what a solution means mathematically as well as visually. Visually, it's very straightforward. So let's take a look at visually. This is going to be a diagonal line. I have a point at 1, and I'm going to go up 2 over 5, down 2, back 5, and I'm going to graph this line. And so I have my y equals 2/5 x plus 1. You always want to label your lines, because when you start graphing big systems and you have lots of lines, you want to see which one is which. You don't want to have the reader of your graph, the person who's looking at this, get confused as, well, which one is this? Because it just looks like a bunch of lines. This one is going to be a horizontal line. At y equals 3. And so the solution is literally just finding that point where they cross. It's right there. That's at 1, 2, 3, 4, 5, 1, 2, 3. So at 5, 3, my solution is at 5, 3. Oh. Now, what this means when this is a solution where they cross, technically what I could do is I could take each of the equations. I could say, okay, if I take y equals 2/5 x plus 1 and I plug in that point of 5, 3, that would mean I would have 3 equals 2/5 of 5 plus 1. 2/5 of 5, my 5's cancel out. So 3 equals 2 plus 1. 3 equals 3. That works. That's a solution for that. The other aspect is I plug into the other one. So if I have my y equals 3, well, I plug in, I don't need an x, I just need my y. So does 3 equal 3? yes, that's a solution for this one as well. So that point 5, 3 works for both equations. That's what it means mathematically to find the solution. The number that makes both equations true. So, not too bad. Does it work differently for lines like this? No, it works exactly the same. So, let's plug a point at 1. If I have a slope of up 2 over 1, I have my graph of y equals 2x plus 1 right there in blue. And then in green, I have y equals 2, and I go down 1 over 1. And so if I graph this, I have this line of y equals negative x plus 2. And now, a lot of you might see the number one problems that we have with graphing equations is my solution right here isn't on any grid mark. So we're going to have to take a guess. 0.5, 1.5. That may be accurate, it may not be, depending on how we know these numbers work, which we'll cover in a later section. This is not going to be at. This time we know our solution is only near what looks like 0.5, 1.5. That may be our answer, but then again, it may not be. So we're going to have to find a method in a later section on how to find when our answer doesn't fall directly on a grid like it did earlier. So the number one thing with any system of equations is most of the time we just want to be able to see what's going on. So two ways to graph this. We can either use our x and our y intercepts by covering up the y, solving for x, covering up the x and solving for y. If we don't remember how to do that, all we're going to have to do is solve for y. So let's subtract our x and divide everything by 7. And let's graph that. So 3, if I have a slope of -1, right there. And over here I have a -8x plus 4y equals -12. Actually, I should have been doing that in green. I'm going to save my solution for red. I'm going to add my 8x, so 4y equals 8x minus 12. Divide everything by 4, 2x minus 3. So up 2 over 1. Let's see. Boom. And so what we notice is that our solution, albeit it looks like it's right on that point, we're not really sure is our graph a little off? Is it actually off a little bit? Unless we actually count. Now this one we know actually is going to fall on the number 2, 1, just because my graph is a little sloppy. But oftentimes, especially when it comes to these half points, you just don't know. Unless you are a very precise grapher, especially if this intercept is way off of the x and the y axis, you may not know exactly where your lines cross. And so this time, I'm going to actually say the solution is at 2, 1. That's the drawback in graphing, is that oftentimes, while these graphs give you a good image of the overall picture, when you zoom in on the finer details, it's not so clear. So let's try one more with lines before we jump off to something else. So with this, what you might recognize is that this is a specific formula that will make your life very easy if you remember how to graph it. If not, you're going to have to isolate your y and graph it. So pause the video, try and solve this, and see if you can't solve it faster than isolating the y. Okay? Let's take a look and see how you did. Now, we know that this is actually going to be in what we call point slope format, which is going to be in something called y minus y1 equals m times x minus x1. And what's so special about this is the fact that our y1 and our x1 are shown. We have a point at x1, comma, y1. And then our m right here is our slope. So no worries, if you didn't know that, this would make your life easier. Let's go ahead and do it the long way, and I'll show you where that comes from. So y minus 3, I'm going to go ahead and distribute my 1/3. So I get a 1/3 x minus 5/3. I'm going to go ahead and I'm going to, let's see, I'm going to do this in, let's do this in pink. And I'm going to add 3. But I'm going to add 3 over here, but I need it to be in thirds. So 3 I know is equal to 9/3. So I'm actually going to add 9/3 over there, which is going to give me y equals 1/3 x. 9 minus 5 is 4/3. So there's my graph. And so when I graph this, 4/3 is not very exact on the graph. So I'm going to go up 1 and over 1, 2, 3. There we go. I get that. And on my other one, I'm going to do the same thing. So I have a y minus 2. I'm going to go ahead and distribute that 2/3, negative 2/3 x plus 4/3. And now here I'm going to add my 2. But over here I'm going to make my 2, which is actually 6/3. I'm going to add 6/3 over here. And so that's going to give me 10/3, which is just over 3. So I get a number right here. And I'm going to go down 2, so 1, 2, and over 3. So let's take a look. Perfect. And we see our solution is right here, 2, 2. And now this is if you had to actually go and isolate the y so that you could graph it. Now remember though, this is in point slope format. So the shortcut is the fact that I could have just graphed a point, let me do this in purple, at my x value, which is 5, 3. So I could go over and say 5, oop, that's directly on my line. My slope is 1/3, so I can't go up 1 and over 3, so I'd have to go down 1 and, yep. I can just look at that equation, I don't need to do any math, and just graph it. The other one right here is I'm going to look at these points and say, okay, I have a point at 2, 2 on my green line, and I go down 2 over 3, which is also on my green line. So if you know how to read point slope, it's going to make your life a lot easier. So that works well. Now, what happens if I don't have just lines? What happens if I have something like an absolute value? Well, let's take a look. This one is an absolute value that's been shifted up by 2. So I have a graph and a graph, and I have a horizontal line right here. So I have y equals 4, and then over here I have my y equals absolute value of x plus 2. This is going to give me not 1, but 2 points. And so this is an interesting subject that we're going to cover later on. With 2 lines, I either get 1 if I have parallel lines. I know those lines will never touch, so there will be no solutions. Or if my lines are on top of each other, I'll have infinite solutions because they're the same line. But those are the only three answers I can get. But if I bend the line, I can get a second answer. And what we'll study later on when we study polynomials is that for each bend, I'm adding another solution. So my -2, 4, and my 2, 4. Every time I bend the line, this absolute value has one bend, I add one solution. So 1 became 2. There we go. And last but not least, let's go ahead and try this one. I want you to pause the video, give this one a shot, and see if you can solve it. Okay, so let's see what you got. This one is an absolute value that's moved down and has a slope of -2/1. So I have something right there. I have a slope of down 2/1. So y equals -2, absolute value of x minus 1. There we go. And now the shortcut way is to look at this and say, okay, I have a point at 1. I know that's actually minus a -3. So I have a point at 1, 3. So let's go to our 1, -3. Oh, it's right there. And a slope of up 2 over 3, down 2, back 3. Ooh. So when I graph my line, I found my 2 points pretty quickly. Y plus 3 equals 2/3 x minus 1. There we go. So I found my two solutions right here and right here at -2, -5, and 1, -3. Perfect. Now the long way, if you couldn't spot the fact that I had a -1, -3, and there's my slope, is you just solve for y. Y plus 3 is distribute that 2/3, so 2/3 x minus 2/3. I go ahead and subtract 3. I know 3 is equal to 9/3, so when I subtract 3 on the left, I'm actually going to subtract 9/3 on the right. It's got to be balanced. They're going to look different visually, but they're the same thing. So y is equal to positive 2/3 x minus 11/3, which I know that -11/3 is almost 4, so 1, 2, 3, almost 4. And I go up 1, 2 over 1, 2, 3. Yep, that's the same line. And that's how you visually graph a system of equations.